Hello. In this video, we will learn about static failure and factor of safety. In this problem, we are asked to find the factor of safety using the distortion energy theory for elements A and B of the bar. And the bar is made of AISI 1006 cauldron steel. Here you have the yield strength, which is equal to 280 megapascals, and the force F is equal to 0.55 kilonewtons, P is equal to 8 kilonewtons, and torque is equal to 30 newtons times meter. So for this problem, first thing we have to do is to draw the stress element A and B. So here's the stress element A, and it's gonna experience sigma and the shear stress. And let's set up the coordinate system. So this is X, horizontal direction, Z, and for stress element B, same thing. You're gonna have sigma and a tau. So let's analyze element A first. The normal stress in element A, it's gonna be equal to the tensile force P over A and the bending moment, so MC over I, caused by force F. So if you plug in the numbers, you'll get 8,000 for P over the cross-sectional area of the bar, which is pi over 4 d squared, plus the moment, which is going to be equal to 0.55 times 100. So let me fix that. Times 100, this distance. And we're gonna convert from kilonewtons to newtons, so multiply by 1,000. And C is gonna be the radius, so radius of the bar over the moment of inertia, which is pi over 64 times the diameter to the fourth. This will come out as 95.46 megapascals. So here is your sigma for tau. So tau is going to be equal to TR over J. So TR over pi over 32 times the diameter to the fourth, and this will come out to be equal to 19.1 megapascals if you plug in the value for the torque and the radius. Okay, remember, do not include the transverse shear at A because it's on the outer edge of the bar. So that's for point A. Let's find von Mises stress, which is going to be equal to sigma squared plus 3 tau squared. If you plug in all the values for sigma, which is 95.46, and for tau, which is 19.1, you will end up, von Mises will end up to be 101.1 megapascals. Remember, this is a simplified version of von Mises stress right here, because this is a plane stress problem. So if you want to calculate the factor of safety, N will come out to be, so it's going to be yield strength over von Mises stress, and this is, it's going to be equal to 2.77, which is larger than 1, so failure will not occur. So let's go ahead and analyze point B. So point B right here, for sigma, it's gonna be only the tensile force, which is P over A being the cross-sectional area of the bar, and this will come out to be equal 25.46 megapascals. And for tau, it's going to be equal to TR, so TR over J plus the transverse shear, because remember point B is at the neutral axis, so FQ over IT. F is this force, I is the moment of inertia, T is the thickness of the bar, which is equal to the diameter. If you wanna, let's have a quick review of how to calculate Q. So if we move here, if you want to calculate Q, it's going to be the area of the semicircle. So right here, area of the semicircle, times y bar, which is the distance from the neutral axis to the centroid of the semicircle, which is given by 4 times the radius over 3 pi. And Q will come out to be equal to 2/3 r cubed. This is the moment of inertia. So VQ over IT, in our case we called our thickness T instead of B. So the final formula will be 4 over 3 V over A. In our case, V is F. And A right here is the cross-sectional area for the entire bar, so pi r squared. So let's go back to our tau right here. If you plug in all the values for torque, radius of the bar, the polar moment of inertia, force F, Q we found, IT. Remember, we found that FQ over IT is going to be equal to 4 over 3 F A being the cross-sectional area. So TR over J, this is going to be tau. That's stress for stress element B. If you plug in all the values, you will end up with 21.43 megapascals So von Mises stress at point B, it's gonna be sigma squared, which is 25.46 squared plus 3 tau squared, which is 21.43. This will end up to be 45.01 megapascals. If you want to calculate the factor of safety using the distortion energy theory, so N is equal to the yield strength over von Mises stress, so 280 over 45.01. This will come out to be 6.22, which is larger than 1. So the bar is safe, no static yielding will occur. Thank you. I hope you find this video to be helpful.